Okay, so let's see about tree data structure. So basically, what is a tree? So a tree is the way of representing data in efficient manner. Okay, when it comes to data structures, we have learned that there are some data structure known as a stack, and there is some data structure known as queue, and let's say arrays and linked list. So those are data structures, and tree is again some special data structure where we can store data efficiently, and we can manipulate with that stored data in efficient manner. So we will see in later this complexity stuffs as well, because as you remembered in the arrays, uh, that basic insertion, deletion, or searching time will be complexity time will be on. So the time complexity will be on. But when it comes to trees, both search, insertion, and deletion will be taken the time complexity of O log n, which is far lower than on. Okay, so basically tree is very efficient data structure than arrays or linked list or any other continuous data structure. Okay, and remember, when we are dealing with such data structures, we have to use this recursion techniques, because uh, tree can grow at any height. So I will explain what is this height mean. So there is no specific height for a tree. You can grow your tree at any height. Therefore, it is better using recursion procedures instead of just using iterations. Okay, so I will explain such stuff in later. For now, just remember, tree is just a special type of data structure where we can store and manipulate with the data in efficient manner. So there are six types of trees generally. So these are the six types: general trees, forest boundary trees, boundary search trees, expression trees, and tournament trees. So in this clip, we are going to look at these binary trees and binary search trees. Okay, so binary tree. So basically, binary means two two ways or something like that. By means some two things, right? So binary search tree means if your tree has some node, then such node can have at most two children and at least no children. Okay, which means null pointers. So this is just an example for binary tree. So in binary tree, there is no specific order that you should store your data value. So you can place your data value at any at the way you like. So one will be placed as a root node, and two will be the left child of the root node, and three will be the right child of the root node. So T1 means basically left child, and T2 means basically right child. Or someone can say that this left child is the root of the left subtree, and someone can say that this T2 is the root of the right child, the right subtree, because we know that since this whole thing is a tree, and if we just consider this left part, and 2 as a root, then again this is a tree. So this is some subset of the whole tree. So therefore we know this subset as the subtree of the whole tree. So likewise, this is again another subtree of the tree. Since this exists on left side, we name this as a left subtree and this as a right subtree. And again, you consider choose color. Again, we can choose this side. So again, this will be left subtree, and this is a right subtree, and this is again left subtree, and this is a right subtree. So this will propagate up until it reaches to the leaf nodes. So leaf nodes basically this last level. Let me erase it as we draw it. So leaf level means basically this last level. So these are known as leaves. When you are reach leaf nodes, there is no subtrees, right? There only exist leaf nodes. Okay, so that is basically binary trees. There is only two children per node, and it can grow at any height. Now, so there are some efficient binary trees. So binary search tree is one of the efficient type, and AVL trees and back trees. We will discuss this stuff later. Those are kind of complex than binary search trees, but binary search tree is the most simplest way of binary trees and some kind of efficient types of a binary tree. Right? So let's look at binary search tree. Uh, So we know that in binary trees there is no specific order that it should be organized the data values, but in binary search trees there is some order. So the order is, so this is the root and this is the data value of the root. So if you are inserting some new node with some new data value, then if your data value is less than root's data value, then it will pass to the left subtree of your tree. And if the x is greater than your root's data value, then it will be passed to the right subtree. So likewise, until it reaches to some leaf end, it will pass down to your tree. Then when it encounters some valid position that it can be stored, then such value will be placed to your tree. Okay. So that is the basic idea about binary search trees. Only difference is there is a specific order when it is storing the data. So all the lesser values will go to the left side, all the greater values go to the right side. So let's discuss some example about binary search tree insertion. So suppose these are the sample data that I am going to insert, and this is the default root as 45, and when I'm inserting 39, so basically 39 is less than 45, so it should be placed over here because there is a null space, so the value can be placed. And since 39 is less than 45, that the specific value will be placed this left side like this. And again 56 comes, so 56 is basically greater than 45, so it should be stored in the right side like this. And remember, when it comes to 12, it will be first check over here. So remember, each and every insertion, it should happen from root onwards. Okay? You can't insert some value from over here onwards. Okay? When you are inserting a new value, it should be start from root and pass to the relevant location. So basically 12 is less than 45, should be passed to the left side, and 12 is less than 39, so like this. So 34 comes, 34 is less than 45, 34 is less than 39, but 34 is greater than 12, so it should be passed over here. And 78 comes, so 78 greater than 45, that's right side, and 78 greater than 56, then right side over here. And 32 comes, so 32 is less than 45, so left side, and 32 is less than 39, left side, and 32 is greater than 12, so the right side, but 32 is less than 34, so left side. The value will be placed like this. So basically that is how binary search tree insertion works, and it's a very simple thing. And in the next video, let's look at binary search tree deletions as well.